Okay, testing. Well, I'm gonna be talking. Slope gate? Did I mistype it? Okay. Um, I can add slope talk into the corner of the screen. Boom. Why is that so ugly? Um, yeah, whatever. Okay, so like I have slopes working. I don't have moving platforms yet. That's a different day. Yeah, there we go. And like it handles all the slopes that you want. Uh, Handles this situation where you collide against the pointy part of a slope. This unwalkable slope, you can't move up it. You slide down it, and if you try to fall from it from above, you can stand on the pointy part of a slope. That bit right there works. This bit right here works. Standing on the pointy part. If you fall down here, you're not actually colliding with the ground, but the game detects that you're not moving, so it lets you jump. And man, this is running really slowly for some reason. Maybe it's just OBS making it run slow. It says it's running 60 frames per second, but it looks very choppy right now. I don't know. It's probably something that I'll have to fix later. Uh, and there's a lot to hear, but I'm gonna just start off with a bunch of MS Paint drawings because a lot of you probably don't quite understand what parts of slopes are difficult. Like, why is it more difficult than having just regular tiles or whatever, and what all the edge cases are. Does the standing still bug still happen? The one where you get stuck? Nah, it's fixed. That was not even part of the slopes. That was the cause of that. That was just the character's speed was getting very low, and when it reached a certain point, it was trying to normalize the speed for which was needed for some operation, was resulting in it becoming infinitely long because it was dividing by zero. And I had a bug where I was checking whether x and y were both zero instead of checking whether the value returned from length was zero. So x was non-zero, but when you tried to calculate the length, it told you that the length was zero, and then it divided by zero, and you got an infinitely long vector. Anyway, I'm gonna close my window so I don't annoy the neighbors. Oh shit! I bumped my monitor. There we go. Windows closed. Neighbors can't hear me anymore. I don't know how many people are watching because Twitch still says zero, but there's definitely chat. So, yeah. Let me check. Okay. I'm gonna reload the dashboard and see if that helps. Yeah, there we go. Okay, so first of all, the first most important part of getting slopes working is how do you test collision against a slope. So we can back up and we can see how we test collision against tiles, which I'm not going to go too in depth to because there's plenty of resources for tiles out there. But basically, you have your grid of tiles, and I'm an amazing artist, so all these squares are perfectly even. You have your grid of tiles, and you know your tiles are indexed at 0, 0, and goes up to 5, 3, 4, 3. Well, this tile in this corner right here is 5, 3, but this one right here is 4, 3, and this one's 0, 0. So you have all these tiles in the two-dimensional array, and you know if you're trying to test collision against, say, this point right here, which looks like it is like 3.1, 1.9. You floor each of these values to get 3, 1, and then you just look up in the two-dimensional array, you know, position 3, tile 1, check to see if this tile is solid or empty, and if it's solid, you're colliding, and if it's empty, you're not colliding. Easy enough. It pretty much covers, that's all you have to do to test if something is colliding for, you know, square tiles. Now, for diagonal tiles, I have, these are the, you can have a bunch of different shapes for tiles. So I have these shapes, these are my tiles. Now, I'm like restricting it so that every shape has one slope associated with it. And, you know, that can be represented by just, you know, 2 points. So you have a point like this point right here and this point right here. This defines the slope of your tile. So you have, like if you wanted a 45-degree tile, instead of it being a solid tile, you say that this tile has a slope going from tile position 0, 1 to tile position 1, 0. Like this, and the order does matter here. So the order matters that you're going from this tile to this tile, which I'll get into for collision. So when you look up what tile you're getting, you're not just getting solid or empty, you're getting solid, empty, or just whatever shape the tile is using. I'm not storing these slopes in every single tile because I only have 20 or so individual tiles. So I have that in, these are the shape tiles that I have. So this whole tile is one byte. 35 bits of that is used for the shape of the tile, and then 3 bits of that is just used for a tag on the tile, for tiles that would need different collision, like fall through tiles or bouncy tiles or whatever. So when you look up your tile, it'll say, hey, this is tile with the shape of, yeah, this is 45-degree down tile, so this shape is 2. And then it says, so you know that this is tile shape 2, and when you go into, you can look up the data. I have this little bit right here. Tile 2 gives you these 2 points, so 0, 1, 2, 2, 1, 0. That is 0, 1 to 1, 0. And then you can test collision against this shape, which is actually very simple. Like you'd think that you have to test against this triangle, because there's a bunch of existing collision solutions that could say, hey, is this point in a triangle or whatever? But you don't need to do that, because we already know that you're in this tile when we're at this point. Like, we've looked up the tile. We know that the point that we're checking is somewhere within this tile bound. So like, you're never going to have a point be here or here or here or here. You know, you're not going to have points outside of this tile when you're looking for tiles. So you're only going to have points within here. And what you've essentially done by just having a slope through the tile like this is you've divided the tile into 2 regions, which is stuff to the left of the slope. Like, this is a ray right here, so you have all the points that are to the left of the ray, which would be, you know, this is to the left of the ray. and this is to the right of the ray. If we reorient it so that the ray is pointing up, you can see that more clearly. You know, I can't rotate in MS Paint, but you get the idea. If this was 0.5 up, you have a left side and a right side. And then, this is the right side of the tile, so anything in the right side of the tile is colliding with it, and if the point's to the left of the ray, then it's not colliding. And testing which side of a ray. Oh, yeah. I'm just going to shrink my webcam a bit. I couldn't find how to crop the webcam in OBS. It just, I looked for like 5 minutes, couldn't find it. But yeah, testing which side of a ray a point is on is a very simple operation. You take the, from the origin of the ray, you take a vector to the point that you're testing, and then you just cross product it with this vector, and if it's positive, you're on one side, and if it's negative, you're on the other side. And that reduces down, I'm not going to close this because I'm going to keep using paint. That reduces down very, very easy. Like, this is the entirety of like whether or not a point is in a shape. Can you read this, or do I need to zoom in my code? Yeah. This right here is the entirety of because I'm like pre-caching the normal for the tile, and like when in the constructor for this semi-solid data, I compute a normal, which is just, instead of having a ray, you now have this. Yeah, you have this normal, which is really just stored from the start, and then you actually just do the vector that I mentioned before, and you dot product it with the normal, and then if it's greater than 0, it's on one side, and if it's less than 0, it's on the other. So it's literally v dot n is less than or equal to 0, where v is just a point minus the start point, and normal is literally a pre-calculated normal for the tile, and then a dot product. And then there you go. You know whether or not your point is in a tile or not. That is very simple. The most annoying part of it is literally just entering all the data for the shapes of your tiles. But once you're there, it works super, super robustly. You can look up a point, and then you can test whether or not it's in a tile. Test collision. Yeah, ignore the rest of this stuff because this is an infinite tile map system, so it first has to find what chunk you're in. But either way, you get the tile, you get the this right here is just a quick way of getting the position within a tile. And then that's it. You get the tile, position within the tile, and then a dot product, and then you'll know whether or not a point is in a tile. That's the easy part. Raycasts are another issue. So the way that raycasts work in a tile engine is, I've redesigned this a few times because I've found myself writing the same raycast algorithm or copying, pasting it around, and every single time I write a new kind of tile map that I've abstracted it a bit. How do you deal with tiles that don't have a single normal but multiple through? None of the tiles do. Like, that's just what it is. None of these tiles have more than one slope in them. They all have exactly one slope. If you want to have a tile that has, if you want a tile that looks like this, you want to know what you do? You use 4 tiles instead and make your tiles half the size. That has 2 normals? What has two normals? This is one normal. These sides don't matter. Yeah. So you just, like, there's, if you want a curve, it starts getting more complicated, but I mean, the point of the matter is that once you have your position, I just closed paint tab. Once you have your position within the tile, you can send that code off to any other algorithm that you want to test it, but I just, one slope through a tile, dot product, simple as possible way. I mean, you could put a bitmap image in here, and then you could, you could have tiles that have weird shapes, like you could have like weird shapes like this, and then you could look up your point within the bitmap that's represented by the tile and get collision that way. Like, you can do what you want at that point. Important part is that you're just testing within a single tile. And so raycasts are part of the reason why I only want to have one slope in the tile. So with a raycast, you have your grid of tiles, and I really should just copy paste a grid from somewhere. Yeah. There we go. I did not want to open Steam. I wanted to open another instance of Paint. Just save this to the side so I can get a grid whenever I want one. Okay, so raycasts is you have a point, here, and you want to raycast it from here to, say, here. So you take a line from that point to that point, and you want to basically test collision against every tile that this line touches. And I don't really want to get into the algorithm behind that. It's because this is, again, not about slopes, but the way that my raycast system works is that for each tile that you have, like, the raycast will report back the current tile that it's looking at, the point where the ray enters the tile, so that point right there, and the point where the ray exits the tile. So where the ray enters the tile, where the ray exits the tile, and it also tells you the direction that the point, like which side you entered from, so that it can then check this next one, and if it knows that it entered from this point, that the ray is going in this direction, the way that it finds the exit point is it tests when it crosses this line and when it crosses this line. Yeah, test when these, like, it counts this point, and whichever one is closer is the one that it uses, roughly. But you go through all of these tiles one at a time. Like, you're in this tile, and with just solid grids, if the tile is solid, then you know that the ray collided with the tile at this point, and you know that the normal, like the surface normal that you collided at, is just the opposite direction that the ray entered the tile from. So hopefully that makes sense. Like, let's say if this tile right here was solid, as you're stepping through the tiles, it's like empty, 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 and then it hits this one solid. It knows that it entered from above, so the surface normal is an arrow pointing up, and you know the exact point that you hit the tile, and that's a raycast. Now, when we have our sloped tiles are stored like, this right here, and you have a slope through the tile. Now you have a left side and a right side of the tile. When doing the ray cast, you know the point that the ray entered the tile, say right here, and you know the point where the ray exited the tile, right here, and you have this line right here. This is the ray. It entered this way and it exited this way. There's 3 cases that happen here, which is 1, the point where you entered is not in the tile, and the point where you exited is in the tile. Again, you can test whether or not a point is in the tile with just a dot product against the normal here. So you're testing whether or not these points are on different sides of the tile. Then you know that the ray crossed over the slope in the tile. If both points are on the same side, and that side happens to be the I'll use blue points. Like if you go from an empty point to an empty point, the ray did not collide with the tile, and you treat it like an empty tile. And then if the ray goes from a solid point, or if it starts at a solid point, like it doesn't matter where it ends in this scenario. If it starts at a solid point, then you just know that it is, it entered the tile on one of these flat sides, just as if it was a large solid tile. So 2 of these scenarios are exactly the same way to handle it as if it collided with a solid or an empty tile. Like, easy enough. The blue scenario here, this is the empty tile scenario, and then this is just you treat it the same way that you treated a fully solid tile. So the only weird one is where you entered on a open edge and exited on a closed edge, in which case you need to find the collision point right here. We already know that the normal of the tile, because that is just stored in our tile data. So all we need to complete this raycast is to get this collision point and just send it back with this normal. That is a line intersection test, and it's really hard to find my code when it's all zoomed in like this. Point collision test is it's that. I probably copy-pasted that from somewhere. But that is the point collision. It's just a bunch of math. It's like, you're not going to rederive the math for this kind of stuff. You're just going to go look it up. Okay, so here, the reason why... you can use a sprite mask within a tile. Like I said, people are discussing this again. So you can use a sprite mask within a tile, but then you lose the ability to get this sort of raycast thing. Like, instead of being able, if in... it makes it harder to test points on the edge of the tile. So you have to make sure that your handling for edge points is correct, because that matters for raycasting. Because you're going to be testing this edge, and if you have an off by 1 issue or a floating point rounding issue, you might be testing for a pixel out here or a pixel out here in that situation, when you really just want one on the exact edge. So when you're in the tile itself, you would then want to make sure that you find the right collision point. And additionally, you kind of want the surface normal as well. And if you have a sprite instead of a tile, finding the surface normal is not easy, because you could have a shape like this, and you don't have any normals stored on that shape, but you could you could store normals on the shape, or you could test a circle around it just to average it out, but it's not going to be perfect. But you can do what you want because you know that there's only one situation where you have to use this advanced thing, and you know that it's going to be the last part of your ray. Well, no, actually you don't, because you would then actually have to do a raycast through the, like, it, if you had a collision map in your tile, you would have to, like, there's, you can't just rely on the beginning and end point. Because you could have a situation where your tile's collision mask looks like, you could have a situation where this is what your tile's collision mask looks like if you're using sprites, and then you could have a situation where the ray enters here and exits here. Ray enters here, ray exits here. And in my tile system, if the start and end point are not colliding with the tile, then you know that the ray did not collide with the tile. So if you have a sprite mask here, then you can end up with situations where you are empty on both sides and you don't know that you are. And you'd have to just ray cast the individual tile itself and every single time, unless you know it's empty completely. You can get around it by making sure that you only have convex shapes within your tile, but then you're like, what's the point of using sprite masks for your tiles if you're only ever going to do convex shapes? No, convex shapes are this is a convex shape, and this is a situation where the line can start and end outside of it. Like, it's weird, it would have to be only concave shapes. Yeah, if it's only concave shapes, then you can know that you, like, because this is a concave shape, then you can know that if you started on one side and ended on another, that you didn't collide with it. You could stop the ray tracing itself only for that tile. No. Yeah, you can, but you would have to do that for pretty much every, like, I mean, then you're doing another raycast, and you have to solve this. You have to do a raycast eventually. Like, I'm not interested in that too much. It's complicated. Trying to get the surface normal on these is complicated. I can always do it later on because the system's pretty flexible. And annoying to redo this kind of stuff, but it's not like when you say costly. This is very fast. You can do 10,000 of these a frame and not even notice it, so it's not like an issue. How do you deal with an AABB when two collider points on the bottom left? Just wait for it. This is the whole. I'm going over everything about slopes. Okay, just wait. We're gonna cover it. So we have raycasts. We have point collision tests. We're missing the ability to do circle casts, box casts, and polygon casts. But that starts getting complicated. So I'm going to come back to that in a bit. But I don't want to close out MS Paint right now. So for my sanity, I'm putting this back at 100%. And I'm going to talk about how old school games did slopes. Actually, we're doing paint again. So the way that old school games did slopes, which include some of the Flash games that I made when I was like 15 years old. Tyne did not use Box 2D. Tyne used my own collision detection thing. You don't want to use Box 2D for platformers. I've tried. It's impossible to make it feel good for like a tight platformer. Like every single platformer you've ever played, if it's like a floaty momentum-y platformer, chances are it probably used a physics engine. Could have not used a physics engine, but if it's like floaty and momentum-y, that's the type of stuff that a physics engine is meant for. But if you use if you played a platformer that has like tight controls and solid collision and all sorts of crazy stuff like The End Is Nigh or Celeste or I Want to Be the Guy or whatever, they're not using physics engines for that. Physics engines have a lot of issues. I'm going to get into what some of the issues are. Circle casts are easy, now they're not. Yeah, so the way that old school platformers did slopes is that you had your character right here, and he's not actually a box. Like the box, it's a lie. He was actually just a couple of points along the edge of the box. So you had a couple of collision probes. So you have 4 collision probes like this. And this is the bottom collision probe, the right, the left, and the top. And every time you want to move the character, you have let's say you have a, I'm just gonna, let's just use a fat paintbrush. This is your character right here. It's 4 dots. And you have a bit of terrain that looks like this. Or something like that. So every time you want to move the character, what you do is you move the character, and then, God, MS Paint sucks because it's dragging the background around. The End Is Nigh was tile-based collision, yes. It was only squares. There were no slopes in it. I'm going to talk about how I did the collision in that because it matters as to why. Because there's differences between how you handle slopes and how you handle, if you just have solid, just square tiles. So the way that this works is you have your character right here. You move him into the, you move him, he wants to move, let's say, he wants to move down and to the right. And then his end result is something like that. That would actually be a degenerate case. But yeah, let's just move him closer to the wall. And you move him, and after movement, he has moved down a little bit because of gravity, and he's moved into the wall a little bit because you moved to the right. Now, the way that the collision probes work is that this is the right side. So first you move the right side to the left until it's no longer colliding. So the whole character moves to the right because this probe is in the wall, and it moves 2 or 3 pixels to the right till you're no longer colliding. Then you do the same for the left. Then you do the top, and then lastly you do the bottom, and it pushes him up and resolves him. And I have that implemented in let's see, the classic tile collider is what I called it. So this is just the character's 4 points, and if the top, bottom, left, right. Hold on. Give me a sec. I forgot to also change the collision response for it. If the bottom's colliding, you're touching the ground. If you're the left or right's colliding, you're touching a wall. If the top's colliding, you're touching a ceiling. That's it. So, does this show up at a good size on the stream? Can you see this guy's dots? Or do I need to zoom it in? Because I can zoom it in. I just gotta not zoom out the camera. Yeah, can you see the dots now? All right, hold on. Give me a sec. I apparently forgot to test. I forgot to check this. Let's just draw a solid circle instead of an outline circle. That might help visualize it better. There, you should be able to see the dots now, right? Yeah. So as you see, if the bottom, like, it works very well. So like surprisingly well. It's a real simple collider. I'll touch over the code in a bit. But, you know, it's handling everything about him just about as good as you could expect. The slopes are handled properly. That's weird because I'm not sure exactly why he's, like, sticking to the ceiling like that, but it's probably just gravity's not catching up to him. You know, the bottom slope down, it has some issues, like, you know, if the left or right side collides, maybe this will be easier if you see him in slow motion, but it kind of, like, pushes him out. You know, if you hit the corners, it's a little, the collision is just a little bit janky. Certain situations don't get handled very well, like that right there. Like, it's kind of weird that you can walk through that, but, you know, the left and right collision probes are not actually hitting the top corner of that, so it considers the fact that you can just go through it. This situation right here is, like, you can't really, like, this is, yeah, it just doesn't, he goes through walls, but if you avoid all those, like, degenerate cases, it actually works okay. And you can make it better by using more than one, like more than one collision probe on each side. So we can do that by, I'm just going to keep the ones that are in the middle because it doesn't really matter how many there are, but then you can also add, like, I want to add some octagonal points, so that would be like, I'm sorry I didn't prepare the 8-point collider right away. I probably should have. Yeah, I'm gonna get rid of the middle points because it'll emphasize one of the points I want to make. I think that probably is the right amount of points. Stickiness caused by maintaining upwards. No, his upwards velocity is being zeroed. It's just that it takes a while for gravity to, like, if you're moving faster than gravity is, then you kind of looks like you're sticking to the wall. Yeah, so here we go. We got eight collision points on the player, which handles a few situations better. This situation still doesn't because, like, you know, you can probably just see what's happening here, especially if I put it in slow motion. Like, the one collision point no longer collides, but because there's a gap between them, he kind of snaps down, and he has this sort of, like, wavy movement on, like, a peak of a spike or whatever. This one should probably handle certain, like, it really depends on the spacing of your points. I probably put the side ones too close, but this might handle this situation better. Nope. Yeah, that situation's probably the hardest one to handle in the collision code that I have, but yeah, the collision probes method, this is kind of what all the old school platformers did. That's what, like, you zip through walls a lot, and people did those kinds of bugs a lot. You know, they exploited those in speed runs a lot, but it's not great. Let me just change this. Change the edge collision probe positions and make it a little bit wider again. Just see what it does. Yeah. One of the things is that that is weird because these 2 points are really close to the length of the slope, so it's kind of depends how fast you're moving, which one ends up he'll be pushed up the slope if he moves and the bottom point intersects with the slope without the side point intersecting, and he'll be repelled by, according to the wall, it's a wall if the side point is intersecting. And it doesn't really, if the side point's intersecting, it does that before it does the bottom point. So if you have it's the situation where you have a wall here and then your side point is in the wall. The bottom point could be clear, it could be underground, doesn't matter. It first will push the entire player out of the wall, so it'll push that point there and it'll push that point there, and then it'll check the bottom to see if that's colliding, and then it'll push that up, and then it'll push that up. The order that you check matters for this collision method. But this is pretty much what all my old school platformers used. Shouldn't the bottom points be on the corners? Absolutely not, because that is the you need, if the whole point of this system is, and I accidentally closed my MS Paint window. The whole point of this system is that the walkable range that you have is essentially if you have these points right here defining your character, the maximum walkable slope is this. Because if any slope steeper than that, the side collision probe will intersect a wall before the bottom collision probe does. And you want, I guess you could put the bottom points on the corners and not also have the side points on the corners. I usually keep a little bit of a but yeah, no, it's actually, this isn't even the maximum walkable slope because it also depends on how fast you're moving. Because if you're moving too fast, you can end up in a situation where the character ends up on a slope that looks like it should be walkable. This should be a walkable slope. But if the character moves fast enough to end up in, I'm going to make that black to be clear. If the character moves in a fast enough speed so that they have all of this intersecting with this slope on a frame, this is treated as a wall because this one is colliding with the wall. So what you if you actually want to calculate your maximum slope, it's this line, but you also then need the character's maximum move speed. So it's really this line is the maximum walkable slope, where this vector right here is, or this vector right here is the character's maximum move speed. So really, this is kind of the actual maximum walkable slope that you have. But that's not that big of an issue, because you can very easily change your character's maximum, your character's max move speed. It's very easy to do. See this one, that he should be able to walk up this slope, but I can't quite tell if this is actually a 45-degree angle. I don't think it is. Oh yeah, it actually is a 45-degree angle, but let's just, move it up. Move these up just a little bit so that it's about 45. This is still going to have an issue because he's even though the angle between these is probably 46 degrees, he moves too fast and he still gets stuck on the slope a bit. Now, he's not actually... hold on. Let me just disable this bit of code real quick. I'm gonna get back to this code later. There's a lot to get over, so just if you are like talking about SAT or GJK or whatever, I'll get to it. There's a whole bunch of other stuff to go over because I'm just starting with the simple stuff. Yeah, let's just make the characters max speed. Alright, fuck, move speed. Yeah, let's just make the characters max speed something ridiculous like 80. Okay, now this is absolutely just going to send him through walls, and he's not going to have his collision resolved properly. This is expected. Yeah, he just moves way too fast to like have his collision respond properly in that situation. But what you can do is classic tile collider move is like it's saying to move him, you know, a certain distance. But what you can do is you can just say move him 100 times at 1/100th of the speed. And then it'll move him 100 times, but each move step will only be 1/100th of the speed that you want to move him at. And aside the fact that gravity does not catch up, he actually, you know, his collision response with the ground actually works properly in this situation. You know, he's not flying through walls and he's not getting stuck on slopes that he's supposed to be able to go up and down on. So since this is such a fast movement thing, like the amount of steps that you divide the movement into, it doesn't matter. Like you can throw insanely high numbers at this and it probably will work just fine. Like 10,000 move steps, like move him 10,000 times to move him the distance that you want to move him. This is probably still going to run at 60 frames per second. Yep. And it's, you know, it's what you expect. It's the same. In fact, it's literally only using 4 milliseconds out of the 16 that we have to move him 10,000 steps a frame. And you can, like, typically what you're going to do is either dynamically figure out how many steps you want to use. Like, you can measure how fast you want to move and say you know that you don't want him to move more than 1/10 of a unit per frame. The number of iterations to use is just the length divided by 1/10. For the end is nigh, I just did 4 move steps per frame, just a flat 4. It wasn't adjusting it based on his speed or anything, because the moving platform stuff in that game needed to take that into consideration as well. So the actual maximum, like to actually figure out how to divide up his speed properly, you'd have to go and measure Ash's relative velocity versus all of the moving platforms to find out whichever relative velocity against a moving platform is the largest, and then use that to determine how many iterations to... It was complicated, but, you know, just dividing it 100 times works just fine for this, and it's probably fast enough that it's not gonna matter, because we went over, like, how to test collision against... I closed my MS Paint window again. We went over how to test collision against a tile. It's literally just using one dot product, essentially. Like a vector subtraction and a dot product, and those are insanely fast operations. Like, you probably do more than that to render a single pixel. Like you do a lot more than that to just render a single pixel on screen. I might be uploading this to YouTube. Depends how good I think it turned out. I closed my MS Paint window again. Okay, so the next thing is that, like, we went over this situation. Let me just see, since I moved the collision points around. If this actually handles the weird, like, slope, the angled case. It's difficult. You notice that there's another, like, case that this does not handle properly. Yeah, where he can be standing on... It's really hard to do it with this, like, good set of points, but I'm going to just set him back to this other set of points, like the just using 4. That, like, you can end up... So this is not a walkable slope right here. And, excuse me, this character moves way too, like, fast, so I have to step frame by frame to actually get this case to work. Okay, there we go. So, see, I'm standing on a not walkable slope, and it's because only the bottom point is colliding, and the slope kind of ends before this middle point can collide. But, like, if I move a little bit, he then slides down. But there was that brief frame, like, right here. Like, he should be sliding down the slope, but he doesn't. And a funny thing that I'm going to talk about is that I had, like, I implemented this sort of basic version of it, like, this morning just so I could demonstrate it, because this is what all my old games used. Like, all my old Flash games, Aqua Slug, Super Soldier. I didn't make that many platformers when I was making Flash games, so there's like 2 that use this, and I use this kind of collision detection method, or this, like, movement method, because it was very easy to do in Flash. I wasn't using tiles. You could get point versus shape collision in Flash very easily, so I would just, you know, if the bottom point was intersecting, it would just move him up in half a pixel increments until he was not intersecting anymore. And what that let you do is let you just draw your level in Flash, and then it would platform against what you drew, which was cool. You didn't have to, like, do any complicated level editing or stuff. But I implemented this because I wanted to demonstrate all of the edge cases. And when I had it originally implemented and I was using my collision response code from my old, from, like, the good collision detection system, and I was reporting the actual normals that they were colliding on instead of saying that the bottom point has an upwards normal and the others have, like, a left and right normal. Like, when I actually gave this crappy system the good response code that deals with normals and stuff, this situation didn't exist. And I was wondering why he was sliding down the slope when he shouldn't be sliding down the slope. Like, this point is being resolved to the right. Like, why? Like, it's why is he sliding? What did I do? And the actual answer is just that this version redirects his velocity down the slope when he detects a collision. So even with this like crappy point probes, you can still actually solve a number of those edge cases. One of the main ones is just the situation where you collide with an angled platform like this. You know, if you have character code that's like this really should be treated as if this point is colliding, because these two are colliding, and he should not be able to keep moving this direction in this situation, but you can because it doesn't detect a wall until this point collides. But, and I think that I did this on some of my Flash games, you can just detect if both the top and bottom points are colliding, and then you can do a separate path where you see whether or not left or right is the shortest path to resolve, and so you can treat top and bottom as a left-right collision. Likewise, you can treat left and right as a up-down collision, but you do have to then test which collision resolution direction is the shortest. I didn't code that for this right now, but no, I'm not closing my MS Paint window this time. I didn't code that right now, but you can see how that solves some of the edge cases. Still doesn't solve others, like the being able to properly handle these sort of like edges right here. Oh yeah, that's also a side effect of the collision response code, is that he's sliding down that. But being able to handle the, the edge snapping and the ability to stand on these like sharp corners properly is, you can design levels that don't need that. But if you ever want to have a rotating platform, you're going to have that situation, because you're going to have corners in your level. Like if your level never has sharp corners and it only has stuff like this right here, that sort of point probe, like if the point probe stuff will work fine. Like if this is the shape of your level, like this, that point probes, there's going to be no edge cases with your point probes on this level. But if you have like just a rotating platform, like if you have a very simple rotating platform like this, and you rotate the platform so that it's like this, suddenly all of these corners are that edge case, like the case that this system does not handle smoothly. So part of the motivation for trying to find a better thing is that if you want rotating platforms, you need to handle that edge case, and handling edge cases does open up, you don't have to be you can be lazier when designing your level, because you don't have to worry about creating situations that trigger these edge cases if your stuff is just more solid in the first place. I'm not closing my paint window. I think I said I was going to talk for a half hour, and I think it's been like an hour and a half, and I haven't even started talking about like the good collision detection system. Oh, the other thing that this doesn't handle is the point probe thing does not handle very small characters. So if you have like a large character, you're generally pretty good at the point probes, because you can move him based on a percentage of his width or whatever. But if you want like a bullet or something, and all these collision points end up real close together, you have to step him. You're going to be stepping him 10,000 times to make sure that you're getting one edge colliding before another. So the other thing is that the next system is, this is what I wrote this one last year. Let me figure out how to enable it and whatnot. This was the one that I wrote last year when I was experimenting with that bird game, which some people might remember. This is still a point-based one, but every point is treated as a raycast. So this system can work with a single point, which is kind of a, you know, I'll demonstrate it as if the character was a single point. So this one, the character is literally just a single point here. And then I'll demonstrate it. This might break on that weird corner case, but character is 1 point. But this 1 point, you know, resolves with all of these situations. You know, it slides. The character can move as fast as he wants, and it will never, like, tunnel into the ground. The wall jump stuff works properly. You know, it knows the ground normal. Like, if you just look at this red point, I'll put it in slow motion. You know, it works. All of this stuff, the single point platformer, this isn't like 5 points really tiny or anything. It's not using a million iterations or whatever. This just works on a single point. This is surprisingly difficult because, like, how do you like resolve the character collision when it's just a single point? And the answer, like, if you have a single point and you move it into a platform, like let's say you have a corner like this, which happens in everything, and your character is moving, you know, a little bit of gravity and a little bit of horizontal information, and let's say the character's point ends up right here. Where does the point go? Like, I mean, obviously you know that it should go here, but this is a tough problem because if the point was previously here, and let's say that the point ends up here because he's moving really fast, the shortest distance to resolve would put the point here, but you know that since he started here, that he should hit the ground here and slide over here. So you know that it should be here, but if you just move him and then resolve, he'll end up down here, which is completely wrong. You basically tunneled through the ground at this point. So the way that this system works is that this one prevents the character from ever entering the ground in the first place. This one works by you have a point, and then you have the direction that the character is moving. So you have like a vector, like this. So what it does is that, given the fact that the point did not start collided, it does a ray cast against the tile map, which then gives this point right here. Now, there's still extra velocity here because the character only ended up moving, 0.4%, or, 4 per 40%, which is just 0.4% of the total way down his movement vector line. So you then want to adjust, you want to do this again. Like, you know that there's this much unused momentum left. So I have a collision response, the slide collision response then, the way that this one works is that you have the surface normal that you collided on. So it projects the additional move speed onto the surface normal right here. And then, so you have the next move step wants him to move like this way right here. Oh, this is so weird. Like, this is the next step of the movement thing is from this point to this point, which it then does the same thing. It does a ray cast in the direction that you're moving, which hits a wall right here. and so then it moves the character there. There's still this portion, like this portion of the move is still remaining, which it then adjusts based on the normal of the collision here, which is pointing the wall pointing this way. When you project this vector onto this vector, you just get 0 because they're perpendicular, and it says, okay, I'm done moving. Hopefully you understood that. I was starting to confuse myself about it a little bit while talking, and we lost like 10 viewers, but hopefully it makes sense. If I didn't explain it right, feel free to ask some questions about it, but basically what happens is it just sort of iteratively raycast stuff. So you know, if you had a slope like this and you want to move a certain distance, it like you want to move from here to here, right? So the first thing it does is it raycasts this point, which actually hits here. We have a surface normal here. We know that it didn't complete its move. There's a certain percentage of the time still left. So we adjust the speed based on the collision response that we want for this, which right now is slide. So the collision response we want for this says, hey, here's the remaining, this is the unused move. This is the surface normal right here. Project the unused move onto the surface normal, and then this is the next step. So we then recurse back and do this again. From this point to this point, and then that one doesn't collide with the wall, so we're good. This does require that you start not collided with the wall, which is a pretty significant limitation if you're trying to deal with moving platforms, because you can't guarantee that with moving platforms, because a moving platform can move onto the player. In fact, that's what they do. Like it will move, moving platform, it'll move, it'll be overlapped with the player. All these raycasts will return 0, and it'll be done. Like, that's it. Well, you just can't move anymore. But the way that the system works then is you can, does the raycast only happen on the direction you're moving? Hold on. So this, I have 6 points in the square. Each one of these is one of these sort of, it's doing 6 raycasts at a time and finding which one goes the shortest to determine where to go. This, handles most of these situations. It's fairly robust. It does not handle this case, because, in fact, it handles this case worse than the old school one, because this point is the one being blocked, and it thinks that you collided with the wall. So you just get stuck on these. Like you're done. You get stuck. But the rest of the cases it handles fine. You can move very fast. It's pretty fast. You don't need to subdivide his move steps, because raycasts already sort of act like that. But yeah, this is, it does not handle these sharp corners, but it handles most of the other cases better than the probe version does. In fact, this handles everything so good that the only real difference between this and the good one is that I need solid shape casts instead of raycasts. And if you do that, then you can just use the same code, like the same technique, where you can use the same technique, but if you just use a circle cast instead of a raycast, you'll have like a fully solid character. God, my throat's getting. I should have Bought some lozenges at the store. Just been talking for 2 hours. Yeah. I'll get in a solid cast because that bit gets complicated. So the raycast only happen on the direction that you're moving. Okay, Ether260 says, what I don't get is, does the raycast only happen on the direction you are moving? Okay, so the thing is that ignore the fact that you have speed entirely. Like, just pretend we're looking at one frame. And let's say that the character is here, and the character wants to move to here. That's the only information that we have. The character wants to move from point A to point B, so which is it's a combination of speed, gravity, friction. Maybe your character's animation system has some root motion and it also wants to move this. All I care about is the character wants to move from A to B. Now, the raycast is just simply the line from A to B. And the result of the raycast is this point right here, the point where it crosses the boundary over to the, where it collides with the tile. It's that point and this normal. And also the tile that you collided with, which is used for additional collision. Like, if you had a bouncy tile, you would know that it's a bouncy tile. But that's the only information that you get from the raycast. So from that, we know that, let's say that this distance right here is 5 units. And let's say that he only ended up moving, 4 units. So then we know that there's 1 unit left to finish moving. We know that that this next raycast is, this vector right here, this unfinished move, the point from the raycast to the destination position. So then what we have to do is we have to adjust the destination position because we know that the character wants to be redirected up the slope like this, because that's what the slide collision resolution does. So we project this vector onto this slope, and then we get our new end point right here. And then we want to move from this point to this point. From this point to this point, which is the same operation as moving from A to B. Like, you just recurse it. There's a limit to how many times you can recurse, because if you try to cast into a acute angle, like, if this is your level right here, if you try to cast your ray into this level, you end up in a situation where you're here, and then you slide down here, and then you're here, you then slide down here, collide with that one, slide here, collide with that one again, slide down. Like, it's never going to actually stop. It's just going to, like, bounce its way into this corner, and it's going to take forever for you to actually reach the full distance that you wanted to move. So it caps the amount of times that it recurses the raycast by 10 or so, which is fine. As long as you're not moving really fast, you're never going to get 10 of those, like, collided together. The other part about this raycast system is that you can't overlap. So, and this is an issue with your raycasts, because if you zoom in really far, the position won't be extremely accurate to, it won't be exactly on the line or anything. It'll be, well, if it is exactly on the line, that could count as a collision, that could not count as a collision, depends on how the floating points round. So when I actually move the character to this point, he actually does not move the full distance of the point. It has a very small epsilon that he like, there's like, if we zoom in, it'll give me this ray as the raycast position, but then I'll just subtract an epsilon from it, where this is epsilon, and it'll move him here instead, just to ensure that he never actually overlaps after a raycast, because if he ends up overlapping after a raycast, then you're going to have a bad time. He'll get stuck, you'll never be able to move again. So I have... This is just the normal tile collider. So this is like the... Yeah, it subtracts a very small movement vector from where the ray collided. And this is very small. I'm using doubles, so I have a lot of precision. Which, this is like, if you like use Unity, most of their platformers also have a skin value. Like Unity's default character controller has a skin, and the value they use in Unity is like 0.05, which is ridiculous. Like if we have this at 0.05, you will notice the character not colliding with the walls properly. Like, that's what having that skin like that. Like, it's not uniform, because if you end up doing something, like, you can end up close to the wall, provided that you didn't get there via a raycast towards the wall, like this situation. Then when I try to move into the wall, it resolves me backwards because of the skin. But, yeah, it's... Having too high of a skin ends up causing some other issues, but... As long as it's just enough to make you to ensure that you're not mathematically colliding with the wall, you're good. I've tried. I played around with skin values. Too low, and it can sometimes end up embedding with the wall. Too high, and you notice the skin, and you don't want to notice the skin. So the response force is actually more than the response norm. There's no physics here. This is entirely math. Like, there's no force involved with the collision response, because there's no physics. I have a lot of collision response modes. Like, that is collision resolution mode. I have stop, bounce, slide, keep speed, manual, grounded, const horizontal, grounded, and stop just the X value. Which I don't think that ended up being useful. But essentially what happens is, bounce will... We're like, here's the grounds. You can interpret this however you want. It could be a wall. So the collision response mode for slide is, you have this vector, this normal right here. I'm just going to draw the normal in black. So slide just takes the excess speed that you didn't use, and it projects it onto the normal, or onto the plane perpendicular to the normal. And we know the collision point between the ray and the line. So slide will take this vector right here, just the part colliding, and it'll return this new vector. We just use orange. So the collision response mode says, my system says I have this vector, which is just v. Says, what is the collision response? Like, what is the adjusted vector according to slide, takes V, projects it onto R, and then returns, V prime or whatever. So then this is the rest of the movement in this direction. It also, my platforming system also then adjusts the player's speed according to the same collision response mode, but they are kind of separate. Like the remaining move is not the same as the character's speed because that is stored somewhere else during the move step. You say, I'm going to move this distance. It says, great. And it makes a vector to represent that distance. When it responds, it then, says, I want to move this distance. And if it needs to do it again, it takes the new one and moves it again. Speed gets, I get a callback to my platformer code every time one of these collisions happens, so I can tell it which type of collision to use. I can say, oh, this one is ground, so I mark the character as grounded, etc. You're going to get a bunch of these. You're going to tell him to move a certain distance. He's going to end up having to do this step 20 times, so you're going to get 20 callbacks here, and each one, it's up to the platformer on how to respond to those. But slide does that. Slide keeps speed, does this, but then also makes sure that it's the same length that it was. It'll then scale it to make sure that the length is the same. Keep speed is, I don't think I use it here, but I think I tried it in the bird game to kind of get more Sonic-y type physics, where you don't slow down by moving up a slope or whatever, where it just sort of redirects your speed as if you went around a curved. Like, keeping the speed constant, you can kind of consider it sort of emulating like if you have this collision bit right here, like if you have angled collision like this right here, slide normally makes you have a very tiny movement afterwards, whereas keep speed makes you, keep going up at full speed. So it sort of treats it as if the edge is like curved, kind of, roughly. I also have bounce, which, bounce would return this as your resolution vector, and we can test that right here. Collision resolution mode, bounce. And this should just make the character bounce, probably. I don't know how it interacts with the rest of this shit. Yeah, let's just not have any of the other resolution stuff happen. And other than detecting groundedness, and just bounce them. Boom, he's bouncy. Oh. Oh yeah, that's part of the snapping code. Yeah, probably I'll get into the snapping part of it. But yeah. Let's just not snap the character to the grounds. But yeah, I can just change the collision resolution mode that I want, and I'll get like a bouncy character. I mean, it's pretty cool that I can just change, like, basically 2 lines of code and get a bouncy character instead. I think. But yeah. So I'm assuming you just deactivate gravity if grounded. No. That's the way you do it with the physics engine, but you don't have to. If you have control over how your character responds to collisions, you don't have to do that. I have a collision response mode called Platformer Grounded Constant Horizontal. What that means is that the collision response mode says if you collide with the ground like this, it first zeros the y velocity, then does a it's kind of hard to tell with a vertical one, but it's sort of like slide, but it instead you kind of have to use an angled platform to demonstrate this. So let's say that there's this much excess movement. Yeah, like there's this much excess movement. That's a certain portion of it is horizontal, a certain portion is vertical. So what constant horizontal does is it projects it like this. As opposed to slide, which would project it like this. This just means that, the x distance that you want to move, you move that much x distance, and then it just resolves the rest vertically. This is because this makes it match with how the collision probe method worked. Like constant horizontal move speed, it is completely not physically accurate whatsoever. It also means that, if your character is not moving to the left or right, they are not going to move to the left or right while on the slope either, because it's not doing slide. If they're moving down on the slope, constant horizontal keeps it at 0, and it just says, 0, you're done. There's only vertical momentum here. Slide would normally push them out this way, but this is not slide, it's constant horizontal. So it projects it upwards, and you don't move anymore when you collide this way. This matches the way that the collision probe thing worked, which is how the collision probe thing is how old school platformers worked. So this is the method that you use if you want your game to feel like one of those old school platformers. In fact, I can disable this bit right here, and it will essentially look like that old school platformer thing, like the collision probe version of it. Where, he goes up, down, slopes really, really quickly, but like his horizontal speed is the same in all of these situations. Doing this with a physics engine is incredibly difficult because it is not physically accurate whatsoever. A physics engine is only ever going to do slide collision response. Like, that's what Box 2D is going to do. And I can show you what happens if we change the collision response mode to slide. I need this check here to make sure that I'm grounded properly. Yeah. Let's just say, if you were using a physics engine, you would get something that feels roughly like this. Because the accurate way to resolve a collision is the slide version of it. Yeah, character slides down the slope a little bit. I'm not sure why he zips up and down at a constant speed in this one, but whatever. Oh yeah, he's not using forces, so. But yeah, like it doesn't matter if you're zeroing his velocity when you do this either. Like, because it's the collision detection system will make you slide if you have gravity on. Because what ends up happening is, you know, your character has some vertical momentum and they're against an angled platform like this. So like your character is on here, he moves down into the platform only vertically. Now, a physics system is then going to resolve him perpendicular to the collision normal, which is not the same as, yeah. It's not the same as moving him straight up. Like you have a collision system will be like, hey, what's the shortest direction I need to move to get this point out of the shape? And it's this direction right here. So it moves here. And then you'll have this small movement where it doesn't matter that you have that you disabled gravity or that you have high friction or whatever. You're getting this movement whether you want it or not if you have vertical velocity in any manner. So you've zeroed velocity. The next frame, he has a little bit of vertical velocity because of gravity. Tries to move him down into the platform. Collided, resolves him this direction. He moves a little bit. Repeat. And the end result is that you very slowly slide down the slope. No matter what you do, this happens. The only way to avoid this is to manually disable gravity if you're on the ground and do a bunch of different stuff to control your movement when you're on the ground and have gravity disabled, which can be difficult to properly do. Case in point, if you actually want to move down the slope and gravity is disabled, you move to the right, you then have to either figure out how to detect the fact that you are no longer in collision with the slope and manually determine this distance to move yourself down. So like basically you snap to the ground after movement, which I do in this engine because that is something that you do to make it feel good. Box 2D does not have shape casts built into its engine, just ray casts, and you need to do a shape cast for this to actually work right. But I don't know, disabling gravity always seems like one of those things that is like if you're using the physics engine, you kind of have to do you have to do hacks like this to avoid these sort of micro slidings. And even if you do it, there's still the very first frame that you collide with the ground, you're getting a micro slide. You know, you're getting this slide the first frame, and then gravity is disabled. But then you also have to you also have to then zero out your velocity, but make sure that the portion that if you do want like character movement, that your velocity is angled according to the platform that you're on. Like, it gets complicated. It's better to just have a system that does not require a hack like that to work, because the less hacks that you need in your player logic, the easier it is to just sort of move a player around properly. So really, the goal in a system like in a platformer collision system is that you don't really want your character to care about about this part of it. Like, you don't want to have to be like, oh, I need to stop gravity if I'm on the ground, because that doesn't make sense. Because really, you should be able to still have your gravity on if you're on the ground. The collision system's the one that needs to properly handle this. And that's part of the reason why I hate using physics or platformers, is because you have to be like, all right, well, I have to disable gravity when on the ground. I have to make sure my character's mass is either infinite compared to other things, or high enough that they can push stuff around, and you got to change the values of friction and drag and maybe manually set velocity and all this stuff. And you got to make sure that because physics doesn't update during your game logic, you have to make sure that you have, you know, a bit of your code that's called before physics updates, and then a bit that's called after to handle stuff that like it becomes much more complicated to just sit down and be like, this character wants to move this direction, and then the collision system should resolve it appropriately. Like, that is what this code does. Like, all of this bit right here is like actual game logic. Like, this describes the way that I want the character to behave when they're on the ground, or colliding with the wall, or you know, colliding with a ceiling, or sliding down a wall. Like, that's game logic stuff. Like, that is part of the player's character feel, so that belongs here. Trying to stop gravity on the ground so that the character doesn't slide down a slope slowly, that's not part of the player's game logic. That's not like that's not something that you, like, unless you specifically want your character to slide down a slope slowly, it should just not do that by default. So that's the whole point of trying to make like a good, like, slope system. Oh, I haven't even gotten into the shapecast stuff, but I think that's next. Yeah, alright. The shapecast version of this. This is the one that I was teasing on Twitter. Oh, what did I do? Now, this is roughly the same method as the point casts, but I'm doing shape casts against the tiles instead. So the character is a solid shape. This, unlike the other ones that I've shown, this handles these sharp corners because, you know, it's a solid shape. Handles those sharp corners, you know, can handle that just fine. Solid shape. Solid shape means that he can't walk through that. Can you see this guy's debug red outline on the stream, or do I need to thicken the size of the line again? You know, this situation. This handles all of these edge cases when you can use a solid shape instead of a single point. But that is incredibly difficult. It's an hour and a half in, and I said I was going to talk for a half hour, but we're just now getting into the hard stuff. So, I close my paint window. So the difficulty with solid shapes is that, one, you cannot use a raycast for this, because while a raycast will hit, like, you know, if you do a raycast from this point to this point, you get, you know, this tile. You get all these tiles in order. You know, it's a very thin line. It's an infinitely thin line when you do a raycast. The math behind a raycast is easy because does paint really only have like a 3-step undo buffer? Alright, whatever. But now if you want to do a shape cast, you need, you know, if you're trying to cast this circle to this point over here, to like this other circle over here, you're not getting just a single line of points. You need to test, you know, all these points. You know, there's a fat set of collision points that you want to test, and they're not really in a natural order like they are in a raycast. Like, there's, you know, which of these points comes first. So you can't just like step through one at a time. So essentially, the first thing that you actually need to do is that you need to find a way to do a shape cast against a poly. You need to find a way to convert your tiles into polygons so you can do polygon collision with them instead of point collision with them. That's not that difficult. So if you have your tile shape and it is, this shape right here, you then, here's the thing is that when you're trying to test a polygon against this, you do not actually know that the polygon lies entirely within this tile shape because the polygon could be partially outside of it. And, if this is the shape you're testing and you're trying to test it against a circle like this, or like a circle like that, this circle, you can't make the same assumption that I made with the points where, you're always within this square. So you want to get the outline of this circle as a triangle, and then you want, the circle that you're testing, and you want a circle to triangle, collision detection test, which is you can use separating axis theorem or GJK or whatever to test whether or not this polygon's colliding with this circle. This is just a test for one tile. So if you're actually trying to test collision against circles against a bunch of tiles, the way that I do it is on demand. You can ask a tile for the polygon that is associated with the tile. So if I ask, I actually have a debug thing for this. Let's see. Yeah. So it's not working. So this is when I'm hovering over a mouse over a tile, it is telling me the collision shape associated with that tile, the polygon associated with that tile, which there's only 20 tile shapes, so I only need to store 20 polygons for this because I can generate the transform on demand, which is easy enough. It's these are the 20 or so polygons that are associated with the tiles. They're in a constant array, and then when I ask for a tile's collision polygon, I just grab the tile's shape and look it up in the tile polygon array. And then to get its transform, I just return a transform that has its X and Y position as the transform. I'm not storing 1,000 polygons in a binary tree or whatever like you would if you were trying to import this into Box 2D, because there's only 20 polygons total, and the only thing that actually changes between those around tiles is their transform, their position. So I say they're generated on demand, but only the transform is generated on demand because the polygons are pointing at the same piece of memory. So you're I want the collision polygon associated with this tile. It will give you that pretty much instantly. It doesn't have to run any algorithms to generate a polygon. It doesn't have to put it into a broad phase collision detection thing, because a tile map already is a sort of broad phase collision detection. But you can just grab the shape associated with a tile instantly, and then you can run it with a collision detection library. I'm using Qt-C2, which is open source. It's on GitHub somewhere that has, collision detection algorithms from, circle to circle, circle to bounding box, etc., circle to polygon, capsule to polygon. It has all the types of collision primitives that you would want out of a collision detection thing. So then to actually test collision, let's say I want to test collision against this circle. This circle has a bounding box associated with it. So I inflate the bounding box by a very tiny amount, which then kind of looks like this. And then all of the tiles that are touching this bounding box are the ones that I test against the circle, which would be all of these tiles right here. And that is just a simple, you get the coordinate at the top of it and the coordinate at the bottom of it, and you just iterate over them in a square. That gets you all of the tiles that are potentially colliding with the circle. You test the shape of each of those with the circle to see if it's colliding. This is much more expensive than a point collision test because, one, you're testing 36 tiles here, and two, the algorithms of testing a shape versus another shape are more involved than testing a point in a angled tile. So it's a lot more expensive, but it's also not that expensive. Well, it depends on the size of your shape and the complexity of it. If you have a polygon, I grab the bounding box of it. This wouldn't apply with moving platforms. It would apply with moving platforms because if a moving platform is also a tile map, then you just run this test on the moving platform. It's like if the tile map has a transformation, the only thing that you have to do is transform, multiply the transform that you have for the shape you're trying to test by the inverse of the tile map's transform before doing any of these collisions. And it'll work fine. You have to do that with the bounding box. You can calculate the bounding box on demand immediately before it. But if this, that's not why moving platforms are difficult. Testing collision against the tile map that is transformed, it's just every single time you ask for a position, multiply it by the tile map's inverse of the tile map's transform, and then you're good. You just run it through the same stuff you were running it before. That's fine. So this is just a test collision. This is not a sweep. This does not give you a cast. To do that, you actually need a time of impact calculator, which time of impact is just you have a circle, and then you have a shape, and you know that the circle has a certain velocity associated with it. Again, velocity is physics, but you don't have to. This is just a vector, like the direction it's trying to move. And you know that that the circle is trying to move to here. Now, time of impact basically moves the circle towards the square in small steps until it collides with the square. And then you have the time of impact that you get is this distance divided by the total distance. So this would be, like a 0.3 for time of impact. And then you also want the, the normal, the surface normal that you get from that, which would be this. And then you want the point that it collides, which is here. So 0.3 is the time of impact here. That he's went 0.3 times the total distance before he collided. So you multiply this original movement vector by 0.3 and add that to the center of the circle, and that will move the circle to this point. And you also know the normal. That's what you get out of a time of impact. Now, C2 has time of impact in it. And it is a very complicated algorithm that goes into a whole bunch of other sub-algorithms, and, it's GJK is the algorithm. That's like the initials of three people's names or something. I've looked into it. I because I know how separating axis works because I've written it before. I have separating axis stuff in my engine that I've written. GJK looks simpler, like to implement. It's harder to understand because it kind of relies on weird proofs. It relies on very strict mathematical proofs to show that it actually does result in what it returns true when there's a collision and false when there's not a collision. But because it's a weird algorithm where it just says do this until you hit a certain result or whatever, and it's not super obvious that always terminates properly, but smart people proved it. They got it to work. I read about it, and when I started reading it, I'm like, yeah, that seems simple. And then it's like, okay, well, to actually get that, what GJK returns is the distance between two polygons. Like, that's essentially what you're going to get from running GJK. And you'll get, like, the distance between them, I think. But to actually get the collision normal and the collision point, you don't get that from GJK from running it once. What you have to do is you have to keep track of, you have to run it multiple times and keep track of how the distance converges on the actual polygon or something, and what you have to run it a bunch of times. You have to keep track of it over time. There's a whole bunch of weird shit, there's matrix, you have to keep track of a bunch of stuff and run it a bunch of times. And so my understanding is that to get time of impact, it runs GJK. It'll tell you the distance between the two polygons. You then move that distance along your movement vector, which is guaranteed not to overlap with the other polygon, because if you moved the absolute perfect direction towards it, you would then be touching the other polygon exactly where the collision would occur. But any other direction, you're just barely not going to make it. You then run GJK again and repeat that process, and you'll very quickly, over a bunch of steps, converge in on the actual time of impact. And I've measured it, and depending on the shapes, it can take anywhere from 3 to 4 iterations up to 20 or 30. I changed the bounds, the precision that I wanted reported, because the initial one that he had in this algorithm did not give me good results, and I also capped the number of iterations to 1,000 because there was an edge case where it was never converging, and it was taking 800,000 steps to actually converge, and now that's no good. But point of the matter is, you get a circle or a shape or any other shape, and you find the time of impact. That's the end result of that. I just did somebody else's code, but it works mostly. Now, because we have this code, very much like our the bounding box thing where you sweep a circle, you have a circle that you want right here. Remember before that the bounding box code would just test collision against these tiles. Now the thing is that we have a sweep test. So we have the circle going from point A to point B, and we want to find a time of impact. Now, I'm doing this very stupidly in my engine, but it works just fine for now, where I just take the bounding box of, one circle, the circle at the start, the bounding box of the circle at the end, and then just take the big bounding box that covers both of those. So we have this circle moving towards this circle, and I just test every one of these tiles that is within this big bounding box. Which is a lot of tiles. I'm not gonna lie. In this scenario right here, this is a lot of tiles that it runs a complicated, multi-step iterative algorithm against to find the time of impact, and it picks the shortest time of impact. So which would be, that's the first one that it encounters. And yeah, this is a complicated algorithm. It's very complicated. It does a lot of tests. It's very slow. But the thing is that it's really the extreme situation, the extreme scenario here is when it's moving at a diagonal. Because if it's moving horizontal or vertical, it's testing essentially all of the you're not going to get more optimal than, testing all of these tiles if you're just testing, like if this circle was moving here instead, you're not going to be able to test less tiles than this bounding box right here. Let me just do this. Like this is about as optimal as you get if you're just doing a completely horizontal cast. This is not that optimal because there's like this whole, I really should be able to do a better sweep and just not have to cover this side or this side. Like I really should be able to get just the ones along the line. But they were talking about a move. We're using this for a movement system for a game. You're not moving 20 tiles in one frame. You're moving half a tile in one frame. So I have not bothered to optimize this, and I probably would not optimize this because I'm not testing large diagonal distances. Even if I was testing 10, that's not that bad if it's fully diagonal. But anyway, you time of impact against every single tile in this bounding box and find the first tile that you hit, and that is your result. I'm not closing paint. And that looks like testing every single tile with, this is a utility or whatever, but you get the collision poly, you get the transform, you shove it at the time of impact calculator, this is, when you can optimize it obviously by just saying, if you've already found a tile that collides at 0.5, you can then adjust that you can iteratively adjust how much you're moving. So like if you if you're moving like here, which is a distance of 1, and then you just, while iterating through tiles, you find a collision that, it collides with this tile right here. Your circle now has this time of impact right here. And so you can, this is a T of 0.2 or whatever. So then you can safely you can readjust the bounding box that you're searching to just be this. So it can shrink pretty fast if you're iterating in the right direction. So it's not that difficult to optimize it. Like that's just a very simple, naive optimization. I'm not actually changing the bounding box there. I'm just changing the maximum distance that I'm shoving at time of impact, which causes it to terminate earlier. But easy enough. One of the benefits is that the result of this is the same as a raycast result. So the rest of the game logic can utilize the shapecast's results in the same way that it handled the raycasts for like the point outline. I forget what I even called it. The last one that I showed that is not the collision probes version. But yeah, it handles it all in the same way, and so that version and this version's movement are the same, except for the fact that I get better collision out of this one, which is what lets me, I just get more solid collision. So, I can collide against these corners. Like, I can wall jump off this corner. Like, it handles everything that you want in terms of collision. Mostly. There's some issues that you still have to deal with manually. But you know, it's a very solid system. It does not. It is very. This and the point set one are very not good for moving platforms. So, but I have not done moving platforms yet, and so I'll get into that later. As in later, as in not today, but here I can just to show you that this works with any solid shape. I have prepared one that, or a version of it that works with a circle. Character's not a circle, so I'm going to turn on debug so you can see the character's circle instead. So, you know, this character is a circle. You know, he collides like a circle, but again, the collision response code is all the same. So, you know, the collision, he's a circle, but the way that he responds to collisions is the same. This does, having a circle makes him not be able to stand on corners because at some point, like, let me just... like, on this corner, the circle's normal means that this is not a walkable slope, so he slides off of it. And he kind of, you know, it's... But this is how you would expect the circle to respond to all of these scenarios anyway. Like, you're using a circle because you want this kind of stuff. Like, you want him to handle corners smoothly or whatever. I personally do not like it when a character can, like, slowly slide off an edge of a shape, which is why I don't like capsules. Like, you can tell sometimes 3D games, like, you can kind of tell when a character is using a capsule because they exhibit this behavior on edges where they, you know, they move down into the platform a little bit and slide off like that. But, you know, circle works fine. I also have, you know, you can set any polygon you want on this type of collision because it's using, as long as you have polygon shaped casts. So here's one that uses a diamond. And this one has an issue, but I'm not gonna... I found this out because I added this, like, right before I started doing the stream. Like, this character is diamond shaped. This character, this slope right here is not a walkable slope angle. So moving the center off at all causes him to slide down. But, you know, the rest of the scenarios that I have here work just fine. The collision normals he gets from colliding with stuff, this is what you would expect out of this shape colliding with a point. Like you would expect him to slide off of the edge like that. You know, the rest of this stuff works. Yeah, that's an interesting one. Like, it's not a great shape for collision, but it is working like you would expect it to work. It does crash if I do that. It's not a crash, it's a purposeful debug break, because that's just what happens if he ends up embedded in a platform after moving, which it's not supposed to do, but for whatever reason, this shape just perfectly aligns with that, shape that he's stuck in. And he gets stuck. I can solve that with some effort, but, you know, if I get rid of the debug break, it won't crash there anymore. But this does happen if he ends up embedded in a wall. And I'm not entirely sure. I mean, honestly, he actually responds correctly. Like, he's not actually getting stuck, so I'm not exactly sure why it was debug breaking there. Oh, it probably... I have a... It's already handling it in a different place in code, but the cast itself was failing there, so who knows. He just looks weird when you press left and right. That's a different thing. Okay, so I'm going to put him back on to his box shape. Well, that was the case. He wasn't actually getting stuck there, but because the way that the code for this works is that it does the raycast, and then, it's not that one. It is this one. It does the raycast, and then it tests the collision of the raycast, and if he was collided, then it tries to move him back. It moves him backwards a little bit, and then if he was collided, if he's still collided, then it just cancels that move. So I'm pretty sure what happened was that degenerate case was happening, and then it would just cancel the move. So no matter what happens, the character will not move into a situation where he is overlapping grounds, because that breaks this sort of raycast system. Because if you try to shape cast when you're already colliding, you just get a value of 0, and so the character never moves. Because it thinks that, well, there's a wall in the way. There's a lot of shit commented out and whatnot. Okay, so there's 2 other things to note about this. One is that snapping the player to the ground after moving, I can disable that and show you what that looks like. So, essentially what happens is if the... Did I close my paint window? Essentially what happens for snapping is if the character was grounded previously, right here. So let's say your character was grounded previously. I'll just use a square to be obvious. And he moved this way. The collision response system will correctly move the character here because there's no collisions in the way. Then, which I've disabled snapping, so you can see what happens where he kind of like falls down slopes. This is being compounded by another system that I have, which I need to disable. It's being compounded with a system that redirects his velocity to match this. But, okay, so... yeah, this means he bounces down slopes, which you can see it's not cool that he bounces down slopes. Like, it feels janky. Like, it feels cheap when the game does this. And I've seen a lot of games, you're standing on a slope and you move left. You press left and then you're in the air, so you can't jump unless you have Coyote time, which this doesn't at the moment, just to keep the code simpler. And then, boom, you try to jump, but you're in the air, so it misses your jump or whatever. But it's janky. It doesn't feel good. So, what you do is, after moving... if he was this only happens if the character was on the ground. After moving, he is no longer on the ground, but he was previously on the ground. So the game does a shape cast downwards to find out how far down the player can move. So it will shape cast downwards. It will get this result right here. It'll be like, oh, I can move this many pixels downwards. I can move this many pixels downwards, and the ground that this collides with has this normal, which is important because you don't want to snap onto an unwalkable surface. Like, I do want that sort of bouncing behavior to happen if you try to go onto an unwalkable surface. But so I have the way that my snap works is here is that I can provide a callback that says, when trying to snap, it says, hey, is this surface normal, walkable ground? And if I return true, then it is. And if I return false, then it's not. And then it snaps the character down. There is a maximum distance that this is allowed to do, which I have set at 0.25. So, if you go over the slope the other way, like if the box ends up over here, this is a much larger distance. This is too large to snap, so it doesn't. And then if you snap, it sets you grounded again. So, not closing pane. So when you have snapping on, it just snaps you to the ground after moving. Makes everything a lot nicer because you're not sort of bumping. You're not bouncing down slopes. You're walking down slopes. And this is why you get this right here. Now, the other thing that just someone mentioned is that, it feels weird to go up a slope at full speed or down a slope at full speed. So I have this piece of code. I know the normal of the ground that I'm on, and this piece of code just sort of, so if I know that my ground normal is this right here, and I have speed, which has, an X component and a Y component. So I split the speed up there. I take the X component of the speed and I rotate it to match the ground normal. And then I add that back onto the Y component of the speed to actually get the new value of speed that I want to use. And that just basically adjusts. So instead of moving, because if it was instead of moving here, which via constant horizontal collision response mode, that would resolve up here and move him. Basically, this is he moves too fast up. Basically, it's just if you're on a slope, it slows you down. I only do it if you're moving upwards because it does make sense that you can go down slopes at full speed. But when you adjust this horizontal speed, you now move up slopes slower and just go down them at the normal speed. It looks more accurate. I mean, you can make it work on both sides of the slopes. I don't need to demonstrate that. The last thing that the last hack, I'm pretty sure this is the last thing I have to cover because my voice is going. I've been talking for 2 hours and 14 minutes now. I don't want to go down slopes at fuller speed. All right, one sec. All right, this should make me go twice as fast down the other slopes. Oh, okay. Yeah, there's some issues. I bugged it out. Yeah, whatever. Yeah. It was doing it when it was not, when he wasn't actually going down a slope. There we go. There. Now you shoot down them slopes. It's not that difficult to just do stupid changes like that. Yeah, you change one tiny little piece. Trying to do that in a physics engine would be insane. You would have so much hacks that you would need to do to get that to work properly if you were using a physics engine. Okay, so the last hack, and I posted this on Twitter, was there's a situation where you have 2 unwalkable walls and two unwalkable walls, and your character ends up stuck between them, such that he's not on the ground because none of these points are colliding with the ground. They're only colliding with walls, but he is also not moving anymore because the collision resolution thing does properly properly resolves this upwards like it should. So without the hack that I have in place to prevent that case, you end up with a situation where Oh no. Well, that's a wall jump, but yeah, that is a wall jump, not a full jump, because he's not on the ground. But, oh no, I'm not on the ground. Now, people discussed this on Twitter when I posted this case, and people were like suggesting stuff like, oh, well, he's colliding with 2 points, and so you can just average the normals together. So you have two collision normals, and so you could average the normals together to get a vertical collision normal, and which would be the average of these two, and then you can be like, oh yeah, I'm on the ground here, and it's like that appears like it would work in this case. It is not obvious that that works in every case, though. Is my camera like out of focus? Did I put it out of focus when I bumped it? Whatever, this is almost done. I'm not gonna worry about it. But it is not obvious that this works in every case. Like, you could imagine a situation where you have more than one contact point on this side right here. You could have a spiky wall like this that had, you could have this sort of spiky wall. And let's just assume that these are like tile points, and so you have a lot of normals like this, and only one normal on here, and so that the average normal would be very close to like this wall side right here. Like, that's a very ham-fisted example of where that hack of averaging the normals together wouldn't work. You could avoid redundantly having normals, or you could eliminate them. But I mean, you could also construct a situation where each of these is 1 degree different, so they are technically different normals. You could manually just check left and right wall, but you could imagine a situation where the character is actually not against a wall and they're against the ceiling. Like, you could have a situation where it's something more like this, where this is an unlockable slope, and the character is collided like this. In a Pac-Man, like, you could, this normal right here, it's a ceiling normal. You could consider that a wall normal as well, but the average of these two could be 0. Well, if they would not be 0 if they were, you would be sledding, but the average of these two kind of looks like it's pointing like that, maybe, which could be an unwalkable slope as well. So really, you have to take a step back and ask exactly what is the issue with this scenario. Like, what is the core of the problem? It's not that you're stuck between two walls that have that's just the manifestation of this issue in this one specific case, that you're stuck between two walls that have non-walkable normals, and so your character's not moving down, but he's also not on the ground, so he's kind of stuck in the air but not on the ground. So when you take a step back and be like, what's the actual core issue? The issue is character wants to move down, character cannot move down. That means that you're on the ground. So the way that I handle this is that before the character moves, I cache their previous position. Just zoom in. So before the character moves, I cache their position, and I cache how much they want to move along the y-axis. Then it moves the character, it snaps into the ground, and then it just checks, did I want to move down? And if I did want to move down, this is the distance that I actually moved. So, previous position, then move the character. So this right here is the distance I actually moved. And then this is 0.001 times the distance that I wanted to move. That should not have a times delta time there. Yeah, I'll just put another. There we go. That's the distance that I wanted to move. So this is a very small percentage of the distance I wanted to move because there are, you're not going to move exactly how down, like you're not going to be, there's situations if you're on like a slope like this where the character wants to move down, but then it resolves them here. And so they move down, 80% of the distance that they actually wanted to move. And you could imagine other situations where they move slower. And you also don't want to just check it at an absolute value because if the character is at the top of their jump arc, they don't actually want to move down that much. So it is appropriate that they didn't move that much. So if they moved less than 0.02% of the distance that they wanted to move, then we just consider ourselves in that stuck situation and mark them as grounded. And this should handle pretty much any edge case that has this sort of symptom where they weren't marked as grounded but were not able to move down. Like it's a pretty robust solution to that problem. And it's a very, very simple solution to that problem. And it sure as hell beats trying to average up all the collision normals together and whatnot. Now, I close paint again, because I thought I was done. But moving platforms now have an issue, though, because... Oh, shit, I'm not done. I forgot to talk about collision resolution with the... with solid shapes. And point sets, for that matter. Collision resolution on a tile map is essentially... if you have a character, you have a circle and it's overlapping a shape, what direction do you have to move to resolve it? And so you have a minimum intersection distance and a normal right here. And so then it takes the circle and it will push it out so that you're not colliding with the shape anymore. Now you can do this between two convex shapes very easily because this is meant for two convex shapes. But if you have concave shapes, it just gets fucking impossible. Like there's no way to do it. And combining multiple convex shapes together into a concave shape, it does not make it easier. Like a tile map is going to have concave shapes. Like here's just one situation that you might want to consider for a tile map is that, this is a concave shape right here. Circle collide like this. How do you find out where the circle go? And, they... you can resolve the circle to this point, and then you can resolve the circle, he still will be colliding with the wall. And then so you can run this code again, resolve the circle in this direction, and then it will be not colliding with the wall. Works okay for that corner, but if you have an angled corner like this, where is the fucking gap that time? Oh. If you have like an angled corner like this, then what ends up happening is that the circle resolves. You have a circle here, circle moves over here and collides like this, so the circle resolves down like, just circle like this. Next step, the circle resolves to not be colliding with this portion of the wall, but now he's colliding with this portion of the wall. So then it resolves the circle up, colliding with this portion of the wall, and then, it has to go down this way, and then it goes up this way, and then it goes down this it takes a lot of steps before you end up in a situation where the circle is no longer colliding with the wall. And I actually have, I'm not closing paint, I have a demo of this just in the like I have a demo of just how the circle thing works with some other code. Based on the collision detection. You see this blue circle, the red circle is the mouse, and the blue circle is where it resolves to. It's not perfect, but it does, it does eventually converge and end up in a not colliding situation. It's not always perfect, it can, it doesn't actually handle cases where the circle is that far intersected with the ground, because then you end up, running into issues with tile seams. It can't find out how to move the circle out of this because it's not colliding with just one convex shape. It's colliding with a ton of tiles. It's not testing a circle against a square. It's testing a circle against a ton of small squares, and the minimum direction that it, the maximum penetration distance in situations like this is that it's going to try and move the circle it's going to try and move the circle to resolve this distance right here, which is kind of weird because it's only checking one shape at a time. So from my experience or my experiments, if you're not, this sort of system works where you just I have another hack, which is that I ignore any resolution collisions that end up on a tile, which is a seam. So I only consider collisions valid if they're normal and their collision point ends up outside of the tile. So it's not. But even then, if the circle is too far in, then it's not going to find any of those, because if the circle's center is below, halfway along one of these tiles, it'll try to push it down and it'll still be collided after it does that. And I don't know, it's a pain in the ass. I probably had more to rant about it. But this is starting to be a lot of talking for the day. Yeah. Anyway, it doesn't work perfectly. So, resolving a collision, what you're actually asking for is, what's the shortest distance that I have to move an object so that it's no longer colliding? And that's very difficult to find out when you're trying to collide against concave shapes, such as a tile map, or a large number of convex shapes that end up being concave, such as a tile map. It's very, very difficult. There doesn't seem to be a good solution for it, other than to try and make sure that stuff never actually collides overlaps in the first place, and if it does, to only have it be overlapped by a small distance so that you can actually resolve it properly. Something that you can do is that you can do point scans to try and determine which, if you have a point right here, if you're just trying to test it as a point, against a tile map to determine where to go, you can do an inverse raycast up in each of the cardinal directions and pick which one is the shortest, so that you would do that. I mean, you can also do some diagonals as well to see if they're the shortest, but you're not going to actually get the exact correct solution in this situation. when I was just testing cardinal directions, which is something that I tried for Mew or whatever, not even with slopes, like no slopes, just check cardinal directions for collision resolution, you have a situation where the point that you're trying to resolve is here. And the resolution directions it checks are these. And it resolves it down here, when it should just go to this point right here, which is at a diagonal. But if you're testing 45-degree diagonals, you actually end up here. So it's complicated. There's no good way to do it. To actually have moving platforms work properly, you need to be able to do this kind of resolution, because you can end up in a situation where the player is standing on a slope like this. Now, a player standing on a slope. And then you have a moving platform like this, moving this way. You know, the player is never moved into a position where he's overlapping with the platform. But then this platform moves into a position where he's overlapping with the player. So in order for the player to actually continue to move, the player first needs to resolve his collision against, you know, the solid geometry properly, which means running that sort of iterative thing that I posted where he, you know, first thing he does is resolve out this direction, and then he's collided with this slope, so then he resolves out this direction, collided with that again, so then it resolves this direction, and eventually it'll find a spot where he's no longer colliding, and then he can do his raycast movement. But because this collision response is just, it doesn't work very well with shapes that aren't circles. Like one of these does it with boxes, and I can show some of the issues with it. But because this collision response thing doesn't work well with boxes the way that I currently have it, and it's really because of the tile seams. Like if the box is just overlapping a little bit, it works fine. But if you start going too far, it's just like, if it's in the middle of a tile, it's trying to push them to the left or right, so it doesn't consider that a valid resolution, and it doesn't resolve it. Moreover, it doesn't consistently resolve on an angle, because you know, the tile itself splits right here. Like the tile, it's this small little bit, and then it's this bit right here. So there's a tile boundary here. So this resolution thing is, it's not resolving the right direction. Like it's not resolving completely the right direction unless you're overlapping. Like even if you're overlapping a little, just a little bit, the blue square kind of goes janky on those tile boundaries. So it's not great, and it also takes a while to converge on these sort of acute angle situations. And it, like, this is a weird, this is just a weird resolution where it's not, where it just kind of went too far because it resolved here and then resolved there instead of, you know, resolving that way. So it doesn't work that great. And it just doesn't work at all if you're intersecting too much. So you have to like limit the speed that your moving platforms move so that they don't overlap the player too much when they collide with him. Or you have to have like a separate case for if you like have a deep collision where you move, you know, if you have a super deep collision with a platform, like, you know, you have a really complicated shape, like platform, whatever, and your character is here, then who knows? Maybe you're just like, all right, I'm very deep in this shape, and then you just want to like test a whole bunch of possible positions in a grid and find and mark all the ones that actually have, this. You want to test a whole bunch of possible positions. With that sweepy thing that I mentioned, and then maybe, it marks these 3 right here as candidates of, these are potential resolve positions, is these 3 right here, and then this one is the closest to the center, so it goes with this one. And then you can like binary search it again. You can start from here and you test a whole bunch of smaller positional adjustments around, like in a 5x5 grid around this one, and pick whichever one's the closest to the original position. Like I've not implemented this. This seems like what you would have to do to actually have a good collision resolution system for this, because you can't really get it out from you can't get it mathematically. Like, you can only do it iteratively, and if it's taking 100 iterations to converge on a if it's taking 100 iterations to converge by just iteratively bouncing the character back and forth between collisions, if you did like a 5x5 search and expecting to find something and then found that and then refined its position a bit, like you can get a better thing with 100 iterations this way anyway. But that is one of the problems that would need to be solved if you actually wanted to do moving platforms, because you need the resolution part, and it's not that easy to do that with this sort of raycasting thing. It's actually pretty easy to do with the like point cloud version, the old school one, because that system is already based around moving and then resolving the collision, but the raycast one is all about moving and never having a collision in the first place. And if, in case you're wondering, the end is now used a point cloud type thing because the character is only because the character in the end is nigh was only using square platforms, you could you could use the 4 endpoints, and what you would have to do is you would move the character horizontally. Like let me just like this is no slopes. So this is Ash right here. Ash wants to move in this direction. And what it does is that it moves him along X first, and then it resolves his X position backwards until you're not colliding anymore, which is very easy to do with just square tiles, because you can just like round his position to the nearest X tile. Or step back 1 pixel at a time until you're not colliding, and then snap forward. And then he moves to Y, where he wants to be on Y, and resolves on the Y. And you do that in 2 steps, and it's perfect collision, no edge cases. You'll be perfectly in line with the ground and the wall. You'll be perfectly, there's no... The points that you're using are the actual endpoints. Like you don't have the sort of like octagon, truncated square shape that you have with the other point cloud thing, where you need to keep this bit open just to handle slopes or whatever. It's perfect on every aspect of it. If he collides with half a pixel of his feet touching a wall, he will hit the wall and slide down. If he's standing with half a pixel of his edge on the ground, he will stand on the ground. It's very simple. It's very easy to do that. That's why slopes are more difficult, because you can't do, this system does not work with slopes. It just doesn't. It would treat every slope as a wall. And yeah, I believe our half hour is up. I might be uploading this to YouTube. I do have OBS recording, so I should have an MP4 of it to upload to YouTube, but we will see. Thanks for watching. You now know about slopes, and I actually did mean to close paint that time. And boom, slopes. Alright, I'll see you in 6 years when I figure out moving platforms.